How do irreversibilities impact entropy calculations? Imagine you are in a kitchen, cooking a meal. You follow the recipe perfectly, but somehow, the dish does not turn out as expected. This scenario can be likened to thermodynamic processes, where irreversibilities play a significant role in how we calculate entropy. Entropy is a measure of disorder or randomness in a system. In an ideal world, if a process is reversible, the entropy change can be calculated precisely. This is done by taking the heat transferred and dividing it by the temperature. In such cases, the total entropy change of both the system and its surroundings remains zero. This means that no additional entropy is generated within the system itself. It merely transfers entropy across its boundaries. However, when we introduce irreversibilities into the mix, things change dramatically. Irreversible processes occur due to factors like friction, unrestrained expansion, or heat transfer with temperature differences. These factors generate extra entropy within the system because some energy is wasted as unusable heat or lost due to internal friction and molecular collisions. As a result, when we calculate entropy changes for an irreversible process, we find that the change is always greater than that of a reversible process connecting the same initial and final states. This extra entropy generation reflects the lost work potential in the system. In practical terms, this has real implications for mechanical engineering. When engineers calculate entropy changes for systems like heat engines, compressors, or turbines, they must consider these irreversibilities. The actual increase in entropy is larger than what would be expected in an ideal reversible scenario. This adjustment is essential for accurate efficiency calculations and performance predictions. The second law of thermodynamics states that the entropy of the universe increases during irreversible processes. This principle illustrates the natural direction of processes and highlights the impossibility of fully returning to the initial state without external input. For example, consider an irreversible isothermal expansion of an ideal gas. The entropy change can be calculated using the formula for entropy change, which shows a positive value. This indicates that entropy is produced due to the irreversibility of the process. In essence, irreversibilities lead to additional entropy generation within a system. This makes entropy changes larger than those calculated under the assumption of reversible behavior. Understanding this concept is fundamental in mechanical engineering thermodynamics, as it sets limits on system efficiency and guides design choices to minimize losses and improve overall performance.